Standard digital credentials operate on a structural flaw. To prove a claim, the system requires exposing the raw, sensitive payload data to the verifying party. Zero-knowledge proofs offer a distinct mathematical alternative. They allow a user to prove a highly specific attribute about their data without ever revealing the underlying payload itself. However, implementing this at scale introduces severe friction. Generating a valid zero-knowledge proof requires evaluating the credential's original digital signatures directly inside cryptographic circuits. In a zero-knowledge circuit, the foundational unit of computational cost is called a constraint. Every mathematical operation adds constraints, increasing the memory and processing power required. Verifying traditional digital signatures like ECDSA or RSA demands an unscalable computational load, requiring upward of 25,000 constraints per proof. Standard mobile devices cannot process this load locally, causing the hardware to fail. Offloading this heavy lifting to third-party servers forces the user to transmit their private data over a network, compromising the trustless nature of the credential. Without solving this 25,000 constraint bottleneck, verifiable credentials remain too computationally expensive for standard end-user hardware. To solve the constraint bottleneck, this implementation substitutes traditional cryptography for snark-friendly mathematical alternatives. Specifically, the architecture utilizes the EDDSA signature scheme, calculated over the baby-jub-jub elliptic curve. This curve is paired with the Poseidon hash function, a cryptographic hash engineered specifically for high efficiency inside zero-knowledge environments. When mapped on the chart, the impact is severe. By restricting cryptographic operations to these specific parameters, the verification complexity drops from 25,000 constraints down to approximately 150. With this reduction, the hardware requirements fall within the capabilities of consumer devices. This optimization ensures that proof generation happens entirely locally, executing directly inside a standard web browser without timing out or crashing. This specific combination of EDDSA, the baby-jub-jub curve, and the Poseidon hash is the same vetted cryptographic stack utilized by leading privacy networks like Aztec and Tornado Cache. This mathematical substitution is the precise mechanism that takes an end-to-end privacy-preserving system from a theoretical concept to a computationally viable reality. Moving from the cryptographic theory to the actual software architecture, the system is divided into distinct, isolated environments. This block diagram outlines the four structural pillars of the application: the issuer system, the user portal, the verifier backend, and the smart contracts layer. These components are stitched together using a modern technology stack, primarily Next.js 16, Tailwind CSS for the interface, and the Noir programming language for zero-knowledge logic. Focusing on the first block, the issuer system acts as the initial genesis point for the credential. The issuer operates as the trusted authority. It intakes the user's raw data, like their birth year, and cryptographically signs it, creating a verifiable credential. Crucially, the issuer must execute this signature using the baby-jub-jub curve. If the issuer uses standard RSA here, the data cannot be efficiently evaluated in a zero-knowledge circuit later. The issuer's sole responsibility is minting snark-friendly trust. Once signed, the data moves to the user, and the issuer exits the process completely. The second pillar is the user portal. This is a client-side Next.js application where the user holds and manages their issued credentials. To validate the credentials locally, the portal relies on Noir, an open-source zero-knowledge programming language. As shown in this flow diagram, the Noir.js library compiles the circuit locally. It runs the logic through Barentenberg WASM, executing complex mathematics inside the browser environment. Because this happens client-side, the user imports their raw credential and private key directly into their browser's local memory. The raw data and the user's private key never leave the local device. They are never transmitted over an external network or sent to a server. Inside this isolated browser environment, the Noir circuit verifies the issuer's EDDSA signature and simultaneously evaluates conditions, such as proving an age threshold. If the math checks out, the circuit outputs an opaque zero-knowledge proof alongside a minimal set of non-sensitive public inputs. The user portal shifts computational power away from centralized databases, executing logic entirely inside an isolated user-controlled environment. Once the user generates the proof locally, it must be validated by the third pillar, the verifier backend. This sequence diagram maps the exact flow of data. In Step 1, the issuer signs the original credential and delivers it to the user portal. In Step 2, the user portal takes that data, hashes it via Poseidon, and generates a cryptographic witness entirely client-side. Finally, in Step 3, the user portal creates the finalized zero-knowledge proof and transmits only that mathematical proof to the verifier backend. The verifier operates in a Node or Next.js environment built specifically to receive and parse the serialized proof array. From here, the backend acts as a router. It can perform off-chain verification directly or facilitate communication with a blockchain network for decentralized consensus. By sequencing the architecture this way, strict cryptographic verification is achieved without a single byte of sensitive payload ever crossing the network. For systems requiring decentralized consensus, the architecture utilizes a fourth pillar, Solidity smart contracts deployed via the Foundry framework. The verifier contract functions as the primary on-chain trust anchor for the system, completely removing the reliance on traditional centralized backend servers. This snippet shows the contract in action, requiring strictly formatted inputs, the opaque proof array generated by Beretenberg, and public inputs like the issuer ID. Like the off-chain backend, the smart contract never receives the user's raw identity data. It cannot read the payload. Instead, the Solidity logic verifies the underlying math. If the snark proof evaluates as true, the contract immediately executes its programmed logic. Upon successful verification, the contract can mutate a specific state variable or authorize a restricted blockchain transaction based purely on mathematical certainty. By anchoring the final validation to a smart contract, the system eliminates the need to trust a human operator to guarantee the credential's authenticity. This architecture illustrates a complete loop. Noir abstracts the circuit logic, WASM executes it locally in the browser, and Solidity provides decentralized consensus. None of these components function together at scale unless the initial constraint bottleneck is aggressively minimized via the EDDSA and Poseidon implementation. By linking these specific technologies, the repository provides a scalable, auditable model for sovereign digital identity in Web3 ecosystems. It is important to note that this codebase is a reference implementation, developed specifically for academic thesis evaluation. Moving to a production environment requires comprehensive security audits, strict key management protocols, and advanced logging infrastructure. Ultimately, this implementation provides a computationally viable, fully verifiable blueprint for the future of trustless, privacy-preserving identity systems.